One of my favorite pieces of generative art of all time is the Rainbow Smoke project by Yosef Fayesh. Rainbow Smoke was initially created as a response to a programming challenge in which the goal was to write an algorithm that produced images where each pixel had a unique color, and every color in the RGB color space was used exactly once. Yosef's solution starts by arbitrarily picking an initial pixel and filling it with an arbitrarily chosen color. From there, the algorithm iteratively fills in all the pixels by expanding outwards from the initial pixel, filling each new pixel with whichever unused color is closest to the colors of the adjacent pixels. I really love the elegance of this algorithm, and I've found that there are a lot of interesting ways to expand on it and apply it in other situations. But before we get to that, let's walk through the original algorithm in a bit more detail. I said before that the algorithm produces images where each color in the RGB color space is used exactly once, but what does that actually mean? The RGB color space is a way of representing colors on a computer, and it works by treating each color as a combination of varying amounts of red, green, and blue. To describe a color using the system, you specify 3 numbers, one for each of those 3 primary colors. Since we're specifying 3 numbers to describe a certain color, you can think of each color as representing a certain point in a 3-dimensional space, hence the term RGB color space. In this 3D space, one axis represents the amount of red in a color, another axis represents green, and the final axis represents blue. Computers can't represent real numbers with unlimited precision, so in practice our color space is divided up into a discrete grid, and it's this fact that allows us to create an image that uses each color in the color space exactly once. We just take each cube in our discrete grid and assign the color of that cube to 1 pixel in our image. This means that the more fine-grained our grid is, the higher the resolution of the resulting image will be. For instance, here's all the colors in a 4x4x4 grid dividing up the RGB color space. There are 64 colors here, 4 to the power of 3, which means that we have exactly the right number of colors to fill up an 8x8 image. Let's walk through how the algorithm would use these 64 colors to create an 8x8 image. The algorithm starts by choosing a random pixel and filling it with a random color from the color space. From here, the algorithm picks a pixel that's adjacent to one that's already filled in. There are 4 pixels to choose from, and the algorithm just makes this choice randomly. Now that it's chosen which pixel to fill in, the algorithm searches through the color space and picks whichever unused color is closest to the color of the adjacent pixels, which in this case just means choosing the color closest to the color of the initial pixel. If there are multiple remaining colors that are each equally close to the adjacent colors, the algorithm just chooses one of them randomly. Now that the second pixel is filled in, the algorithm just repeats this process until the entire grid is filled in, or equivalently, until all the colors in the color space have been used. Now that we've walked through the algorithm for this very small image, let's try it for a much larger image. Here's what it looks like when we apply this to a 64x64 image, which corresponds to a 16x16x16 grid in our 3D color space. As the resolution gets higher, you start to see more interesting structures emerge. Here's what it looks like when we use the algorithm to make a 1920x1080 image, which is the full resolution of this video. As it turns out, we can't really make a regular 3D grid for an image at this resolution, since 1920 x 1080 isn't a cubic number. In cases like this, you can also just randomly sample a bunch of points from the color space rather than using a regular grid, and when your resolution is high enough, the results will be basically indistinguishable. After I learned about the Rainbow Smoke algorithm, I was really amazed by how elegant it was and all the interesting structures that it created, and I got to thinking about different ways that I might be able to use it. After playing around with different versions of the algorithm, I've come up with a few generalizations that I find really useful. I call this new algorithm the Generalized Smoke algorithm, or simply the Smoke algorithm, or smoking, and there are a few key differences between it and the original Rainbow Smoke algorithm. In the rest of this video, I'll describe some of the key differences between the Generalized Smoking algorithm and the original, and show off some of the fun things that you can do with it. The original Rainbow Smoke algorithm assigned 3-dimensional vectors representing positions in the RGB color space to a 2-dimensional grid representing the pixels of an image. The first key modification in the Generalized Smoking algorithm is that the values we assign to our pixels don't necessarily have to represent positions in the RGB color space. For one thing, we could use some other kind of 3D color space like CMY or HSV, but you can also do something completely different and define your own color space using an image. A color space is really nothing more than just a way of assigning a color to each point in some space, and an image is simply an assignment of colors to the cells of some square grid. So it's really easy to treat any image as a 2D color space. The color assigned to a given 2D position is just the color of the pixel at the corresponding position in the image. When you use the smoke algorithm with a color space defined by an image, you end up essentially rearranging the pixels of the original image to form a new one. Colors that were nearby one another in the original image will also be nearby one another in the new image, but aside from that, the structure will be completely different. Rather than using an existing image, you can also just create a new one from scratch that has whatever kind of color palette you're looking for. Since the structure of this image won't be preserved through the smoke algorithm anyways, the image itself doesn't really have to be anything interesting. You can just use some splotches of whatever colors you like. Here's an image I created for this purpose that has a nice pinkish, orangish, sunsetty color palette, and here's what it looks like when you use this image with smoking. By the way, I find this technique of using images to define a 2D color space to be useful all across generative art, not just in this algorithm. So if you haven't tried this before, I really encourage you to play with it. It's a wonderful way to control the color palette of a generative piece. So we can use the smoke algorithm for colors in any color space, not just the RGB color space. But taking this a step further, we can also use the algorithm as a way of assigning things other than colors. When we used the RGB color space, the values that we assigned were technically 3-dimensional vectors, and when we used image-defined color spaces, they were 2D vectors. The generalized smoke algorithm can assign vectors of any size to a square grid of pixels, and those vectors can represent anything you want, not just colors. The artist Sumrav has done some pieces that provide a really excellent example of this, by using the smoke algorithm in combination with flow fields to produce some really neat results. For one thing, Sumrav has explored using a flow field to bias the direction in which colors spread during the smoke algorithm. But more relevant to our purposes, he's also used the smoke algorithm to define flow fields, producing results like these. The flow field in this animation is defined using an underlying square grid, where each square in the grid has a certain angle assigned to it, and particles within a square are pushed along that angle. I've done a recreation of Sumrav's piece that makes this more clear. The squares in this grid are like the pixels of an image, and the different angles given to the squares are distributed just as the colors would be onto a grid of pixels. Though the vector describing the angle is just one-dimensional, as opposed to the 2- and 3-dimensional vectors that we use for colors. I'll make another video soon exploring some more interesting new ways of using this generalized smoke algorithm. One thing I'll explain is how to use the algorithm to define systems that change over time. As a sneak peek for that video, here's an example of what that might look like.